We now start module 5 of chapter 2. We have already introduced the notion of basis of a vector space. We have seen examples. We have learned some basic theorems. Now we are going to understand two very important properties of a vector space. One is that every non-trivial vector space has a basis, and we will be able to show that if a vector space is finite dimensional, then any two bases have the same number of elements. This number is what is called the dimension of a vector space. Let V be a vector space over a field F. Now we prove that if V is non-trivial, that means V has at least one vector other than the 0 vector, and if it is finite dimensional, that means it has a finite spanning set, then V has a basis. Let us recall, a basis is a spanning set which is linearly independent. So you can understand that because of finite dimensionality of the vector space V, we already have a finite spanning set. Let us call this set S. If it so happens that the set is linearly independent over the base field F, then of course we are done, because S itself is a basis then, being linearly independent and the spanning set for V. But if S is not linearly independent over F, then you will see that we will be able to extract a linearly independent subset of S which would also span V. See how we do this. So, let S be a finite spanning set, and S is of course not the trivial one, because then it cannot span a non-trivial vector space. So, there must exist at least one non-zero vector V1 in S. Let us call this singleton V1 to be the set S1, which is a subset of S. Now, V1 being a non-zero vector and S1 being the singleton V1, S1 is linearly independent over the base field F. If it so happens that the set S, that is the spanning set of the vector space V, is contained in the span of S1, what does that mean? That means every vector in S can be written as a linear combination of V1. If that is the case, then S being a spanning set of V and S sitting inside the span of S1, we surely have that S1 spans V, and then we are done, because S1 is linearly independent and it spans V, therefore, S1 is our desired basis. So, if that is not the case, that means if S is not contained in the span of S1, then what happens? That means we have a vector, call it V2, which is in S, but which is not in the span of S1. Let us form the set S2 consisting of the vectors V1 and V2. Once again we have the set S2 is linearly independent. Why is that so? Because otherwise if we do have a non-trivial linear combination of V1, V2, then we can show with very little effort that V2 can be expressed as a linear combination of V1, which cannot be the case because V2 is in S, but not in the span of S1. So, we have a linearly independent set S2. Again, if it so happens that S is contained in the span of S2, then because of a similar argument, the span of S2 has to be V, because S spans V and S is contained in the span of S2, therefore, S2 must span V, and S2 is linearly independent, and once again we are done. S2 is the desired basis. So, if that is not the case, that means if S is not contained in the span of S2, once again we have a vector V3 which is in S, but not in the span of S2. We form the set S3 consisting of V1, V2, V3. A similar argument shows that S3 must be linearly independent over F. So, we continue this process, and at the kth stage of this process, of this iteration, we get a set of vectors, call it Sk, consisting of V1, V2 and so on up to Vk, such that Sk is linearly independent subset of S over the base field F. And at each stage we have to see whether S, that is the spanning set of V, is contained in the span of Sk. Once we achieve that, then V has to be the span of Sk, and Sk being linearly independent, it is a basis for V. Now, we know that S is a finite set. Therefore, it must happen that we reach a stage where either S is exactly equal to some SL. Remember, SL is that linearly independent subset of S obtained at the Lth stage, or we must have that S is contained in the span of SL. If S is equal to SL, then of course we are done, because then S itself is linearly independent and it spans V, therefore, SL is a basis. Otherwise, if S is contained in the span of SL, then we claim that span of SL must be equal to the vector space V. Why is that so? Each vector V in V can be written as a linear combination of elements from S, and each element of S can be written as a linear combination of elements of SL if S is contained in span of SL. Therefore, each element of V can be written as a linear combination of elements from SL. That shows that span of SL must be equal to V. Therefore, we have proved that SL is linearly independent and it spans V. Therefore, SL is a basis for the vector space V. So, this proves that if we have a finite dimensional vector space, that means a vector space V having a finite spanning set S, then we can find a subset of the spanning set S which is linearly independent and which spans V. Let us consider this example, and we follow the same technique that we used for proving the previous theorem, and we demonstrate how to extract a basis from a spanning set S. So, the vector space V in this case is R3 over the base field of real numbers. We have a set S consisting of these 4 vectors 1 0 0, 0 1 0, 1 1 0 and 1 1 2. Now, first of all, this set S is indeed a spanning set for the vector space R3 over R. How do we prove this? So, we want to show that if we take any 3 tuple A comma B comma C, then it can be expressed as a linear combination of the given 4 vectors. So, if you look at it carefully, then we want the 3 tuple A B C to be equal to x1 dot 1 0 0 plus x2 dot 0 1 0 plus x3 dot 1 1 0 plus x4 dot 1 1 2, and the simplification gives you this system of equations, that is x1 plus x3 plus x4 is equal to A, x2 plus x3 plus x4 is equal to B, and 2x4 is equal to C. Now, to show that this set S spans the vector space R3, we have to solve for x1, x2, x3, x4 in the set of real numbers R in terms of A, B, C, and that is fairly simple, as you can see from the expressions itself. Now, let us try to extract a basis out of it, and we will exactly follow the method that we used for proving the previous theorem. Let us take the vector 1 0 0 from S. Call this singleton 1 0 0 to be S1, then S1 is of course a subset of S, and 1 0 0 being a non-zero vector, 1 is linearly independent. It is clear that the vector 0 1 0 is not in the span of S1 for the simple reason that this 1 is sitting at the second position of the vector, and the second position of 1 0 0 is 0, therefore, it cannot possibly generate the vector 0 1 0 through linear combination. So, we can surely include this vector 0 1 0 in our list and form the new set S2 given by 1 0 0 and 0 1 0, and the set S2 is of course linearly independent over the real field. Now, it is time to choose one more vector, and we see that the vector 1 1 0, which is in S, is in fact in the span of S2, whereas the vector 1 1 2, which is also in S, but it is not in the span of S2. Therefore, the set S is not contained in span of S2, and that is because of this very vector 1 1 2. So, we can pick this up, the vector 1 1 2, and take it in our list and form the set S3, which is 1 0 0 0 1 0 and 1 1 2. Now, it is clear that S is contained in the span of S3. Why is that so? Because the only other vector which S has and S3 does not have is the vector 1 1 0, and which is surely in span of S3. Therefore, this is the last stage, that is, the set S3 is a linearly independent set which spans R3, and S3 is a basis of R3. We have proved that every non-trivial vector space has a basis, that is a spanning set which is linearly independent. We now try to understand what could be cardinality of a basis, that means number of elements in a basis. To make it more precise, is it true that any two bases in a finite dimensional vector space have the same number of elements? We are going to prove a theorem which is known as replacement theorem. This theorem will be useful in proving quite a few facts about basis of a vector space. Most importantly, any two bases have the same number of elements. We will also see that if we start with a linearly independent subset of a finite dimensional vector space, it can be extended to a basis. We now prove the replacement theorem, which says the following. Let V be a finite dimensional vector space over a field F generated by a finite set S which has n vectors. Let T be a linearly independent subset of V such that T has m vectors, then m is less than or equal to n, and there exists a subset S1 of S such that S1 has n minus m vectors and T union S1 generates the vector space V. So, we need a finite spanning set S, we need a linearly independent subset T of V. If the number of elements in S is n and the number of elements in T is m, then m can be at most n. This is the first part of the statement, and what the second part tells you is that starting with this linearly independent set T, we can get some more vectors if needed from the spanning set S, so that T union S1 is itself a spanning set of V. Now, we start proving this theorem, and the proof of this theorem is by the method of induction on the integer m. Remember, what is m? M is the number of elements in the linearly independent set T. The initial case is m is equal to 0, that is when T is the empty set. Empty set is surely a linearly independent set for any vector space V, because it is vacuously true. What does that mean? That means we cannot get a non-trivial linear combination for the 0 vector with the help of vectors from T, simply because T has no element. In this case, we can take S1 to be S and we are done. That means the spanning set of V, which is S, that itself serves the purpose. Therefore, the induction begins. Now, the induction hypothesis, which says that we assume that the theorem holds for some integer m bigger than or equal to 0. And now, we prove that this statement is true for an integer m plus 1. That is, if T is a linearly independent set of m plus 1 vectors v1, v2 and so on up to vm plus 1, then we want to prove that the statements are true with respect to this linearly independent set T and the spanning set S. Take v1, v2, vm, which is a subset of T. Since T is linearly independent, the set containing v1, v2, vm is also linearly independent. And this set has only m vectors. Therefore, by the induction hypothesis, m is less than or equal to n, and there is a subset of S, call it u1, u2 and so on un minus m, such that v1, v2, vm union u1, u2, un minus m generates V. In particular, they must generate Vm plus 1, which is a vector in the linearly independent set T. Therefore, we must have scalars a1, a2, so on up to am and b1, b2, so on up to bn minus m, such that Vm plus 1 can be written as the linear combination summation ai vi I equal to 1 to m plus summation bj uj, j is equal to 1 to n minus m. Here we make a few quick observations. One is that n has to be strictly bigger than m. Otherwise, we can see that the second expression of the left hand side, that is summation bj uj, where j is from 1 to n minus m, that will simply disappear, and we would be left with Vm plus 1 is equal to summation ai vi, which would contradict linear independence of T, because Vm plus 1 is a linear combination of V1 to Vm, which cannot happen. And one more observation is that Bi has to be non-zero for at least one I. Again, the reason is similar in the sense that if it so happens that all of B1, B2 and so on up to Bn minus m are 0, then again we will be left with only summation ai vi, and that is equal to Vm plus 1, which would again contradict the linear independence of T. Let us assume that B1 itself is not 0. Therefore, we have on the left hand side U1, which is separated out because B1 is a non-zero element in F. So, we can express U1 in terms of the other vectors. What are the other vectors? They are V1, V2 and so on up to Vm plus 1, the elements of T, and U2, U3 and so on up to Un minus m. Therefore, U1 is in the span of these vectors V1 to Vm plus 1 and U2 to Un minus m. Now, look at this list very carefully. How many vectors do we have? There are m plus 1 of them in the first set, that is V1 to Vm plus 1, and there are n minus m minus 1 of them in the second set, that is consisting of U2 to Un minus m. So, together we precisely have n minus m minus 1 plus m plus 1 vectors. Let us see what that means. First claim is that V1, V2, Vm m plus 1 union U2, U3 and so on Un minus m, this set generates V. Why is that so? Because V1 to Vm union U1 to Un minus m generates V, and U1 belongs to the span of the vectors V1 to Vm plus 1 union U2 to Un minus m. Therefore, the set that we are looking for is nothing but S1, which is the set consisting of U2, U3 and so on Un minus m. S1 is of course contained in S, and there are precisely n minus m minus 1, that is n minus m plus 1 within the brackets, these many vectors, and S1 union T generates the vector space V. This proves the theorem because we have showed that the induction began with m equal to 0, and then we assumed the result for m and proved the result for m plus 1. Now, a very important corollary, let V be a finite dimensional vector space over a field F, then any two bases of V have the same number of elements. We know that any finite dimensional vector space has a basis. We have learned this before, and with the help of the replacement theorem, we can indeed show that any two bases have the same number of elements. Well, the proof is really simple. How to go about it? Remember, any basis is a spanning set. and also a linearly independent set. So, because of these attributes, you can use the replacement theorem starting with two bases, say B1 and B2. Treat B1 as a spanning set and B2 as a linearly independent set. Then you get an inequality in the number of elements of B1 and B2. And when you reverse the roles of B1 and B2, then you get the reverse inequality in terms of number of elements of B2 and B1, which would prove that the number of elements of B1 is the same as number of elements in B2. This allows us to define what is called the dimension of a finite dimensional vector space, and that is nothing but the number of elements in a basis of V. This number, just now we have seen, that is a well defined number, because any two bases have the same number of elements, and therefore we can indeed call it the dimension and denote it as dim V. And now a very useful corollary, which is again a beautiful application of the replacement theorem, which says the following: let V be a vector space of dimension n over a field F. A finite spanning set for V contains at least n vectors, where n is the dimension, and a spanning set for V containing exactly n vectors is a basis for the vector space V. The second part of the statement is that a linearly independent subset of V containing exactly n vectors is a basis for V, and the third part says that every linearly independent subset of V can be extended to a basis for V. All these statements are almost immediate or straightforward from the replacement theorem, and that shows the strength of this replacement theorem. This brings us to the end of module 5 of chapter 2. We have learnt two very important theorems in this module. One is about the existence of a basis in a finite dimensional vector space, and the other one, which is called the replacement theorem, which we used to prove that any two bases in a finite dimensional vector space have the same number of elements, and that number is what is called the dimension of the vector space. Another important fact is that starting with a linearly independent set, we can extend it to a basis of the vector space, and also we have learned that starting with a spanning set of the vector space, we can extract a basis out of that spanning set.